All right, so let's dive right in. Today, we're tackling a really fundamental question. What is physics, really? Is it just a pile of complicated equations, or is there something more to it? Something maybe a little closer to philosophy? We're going to explore the real relationship between the big ideas that drive science and the math we use to write them down. And this right here is the heart of it. When you're trying to figure out the very nature of reality, where do you draw the line? Where does physics end and philosophy begin? Or maybe the better question is there a line at all? You hear this all the time, right? This is the conventional wisdom. Math is the great divider. If you can't write down an equation for it, well, that's just philosophy, not real physics. But what if that's not just wrong, but it's actually holding science back? What if the real story is way more interesting than that? Yeah, we're going to make the case here that this conventional wisdom is just plain wrong. By trying to boil physics down to only math, we actually miss the most important, the most crucial step in the entire scientific process. Okay, so here's the central idea. Before a single equation ever gets written down, you have to have a conceptual model, an idea, a story, really, about how the universe might work. The math doesn't just appear out of thin air. It comes in later to describe that idea with precision. So this process, it flips that common view completely on its head. See, it starts with the concept, the big what if. Only after you have that idea do you bring in the math to give it some real structure. And then, the final step, you have to test that mathematical description against reality. And you always have to be aware of its limits. In this way of looking at it, the idea is king. Now, of course, this isn't to say math isn't important. It's absolutely essential. It's the language we use to make our ideas rigorous, to make them testable. And let's be honest, sometimes that language can look pretty intense. What's the point of all this intimidating-looking math? Well, it's not about being complicated just for the sake of it. It's all about describing reality with incredible precision, making predictions that you can actually go out and test, and communicating these really complex ideas without any ambiguity. If the ideas are the story, then math is the grammar that makes sure the story is told clearly and rigorously. Okay, so that's the language, but what does it actually say? How does all this mathematical grammar translate into actual stuff we can see and touch? Let's look at a couple of real-world examples. Let's take something as simple as pulling on a metal rod. The math doesn't just go, yep, it stretches. It tells us exactly how much it will stretch for a given force. It tells us exactly how much internal stress that material is feeling, and it can even tell us how much energy is now stored inside that stretched rod. That is the power of precision. And this is a brilliant example of how a small change in your conceptual model leads to totally different math. A cylinder and a sphere, they're both pressure vessels. But just because their shapes are different, the way they handle stress is different. The math shows us that the hoop stress trying to burst the walls of a cylinder is actually twice as big as in a sphere with similar dimensions. Now that's a critical difference if you're building, say, a submarine. So we have a model. We have the math to describe it. And the math works. It makes correct predictions. So we're done, right? But is that really enough? Does a correct calculation automatically mean you have good physics? Just think about this for a second. What if the math gave us E equals mc times cubed? As a piece of mathematics, that equation is perfectly valid. But as physics, it's a complete failure because it just doesn't describe the reality we live in. It's a mathematically perfect sentence that tells a total lie about the universe. And this brings us to what you could call the 4 pillars of a successful theory. It's not enough to just describe what happens. A good theory also has to explain it. It needs to give a coherent cause. It has to be understandable, something we can actually wrap our heads around. And finally, the underlying model has to feel plausible. If you miss any one of these, even the most beautiful math is probably going to end up on the scrap heap of scientific history. So what all this really reveals is the true nature of physics. It's not a static book of facts that's already been written. It's a constant dialogue, a back and forth between our creative ideas about the universe and the mathematical tools we use to sharpen and test them. It's a living, breathing process. So, at the end of the day, to just dismiss an idea and say, oh, that's not physics, simply because it doesn't have an equation attached to it yet, well, that's missing the entire point. The idea has to come first. Math is the essential partner that brings the rigor, for sure, but it is not the creative spark. In fact, in modern physics, this sometimes gets taken even a step further. For systems that are just ridiculously complex, like, say, particle collisions in an accelerator, physicists will often build a computer simulation, a numerical model, before they have a nice, clean formula. The conceptual model gets tested on a computer first. That elegant equation might come years down the road, or it might not come at all. And that really leaves us with a final thought to chew on. If mathematics truly is the precise language we use to speak about reality, then what profound, incredible ideas about our universe are we struggling with right now simply because we haven't yet invented the right words, the right grammar to express them?